Today we're going to begin the path of learning about one of the coolest topics in computer science, and that is data structures. But to do that, we're going to need to first learn about abstract data types, which are even more fundamental than data structures, and through abstract data types, we'll see why we even need data structures to exist. So what is an abstract data type? It is an interface for working with data. Now, what that means, an interface is kind of like a set of capabilities or functions that are grouped together in one entity. So let's think of the list, for example. In real life, we have lists of things, right? And we insert things into the list and we remove things from the list. That, in our computers, we're going to represent as the abstract data type known as the list. Let's take a deeper look at the list abstract data type. Like I said before, it's a set of functions all jumbled together into one entity known as the list abstract data type. So why do we need abstract data types in the first place? Well, that actually becomes a bigger conversation that we're going to talk about when we talk about inheritance and the class hierarchy in object-oriented programming. But let me give you a quick example. Let's say I have a telephone, right? Its interface would be the ability to make a call. So instead of insert whatever, you'd see call, and you'd see text as well. So that's why we have interfaces. Again, that's a very quick practical example, and we'll get more into it later. But I just want to emphasize that an abstract data type is pretty much only a set of functions. Now, these functions are actually not defined yet, and that's where data structures come in. A data structure is an implementation of an abstract data type that fills in these functions. And when you fill in these functions, you fill them in such that they have a specific kind of performance or cost. So what do I mean by cost? Well, some ways to implement a list into a data structure can do insertion better than they can do deletion or search. Other data structures that implement that list abstract data type can search better than they can insert and whatnot. So let's take a look at an example of data structures. Okay, so here I have two different data structures that implement the list. And we're going to look at analyzing the array list first. So the array list is what we've been dealing with in Python so far. It's that list with open brackets that we just insert into and remove from and loop through. So first we're going to analyze the search function. And pretty intuitively, when we search for an item in the list, we're going to have to loop through the entire list. And when we find the item, we're going to report what position it's in. So that's the algorithm for searching in an array list. How long does that take to run? That is the cost. Well, it directly depends on the amount of items in the list. Then in the worst case, I'm going to have compared n comparisons to see where z is. So let's say that costs n, where n is the amount of items in the list. And it could be more. If we have a worse algorithm, it could be something like n squared, like we do n comparisons for each of the n items, which would be bad. Okay, let's look at insertion now. So when we insert an item into a list, let's say we want to insert an item after x. What we do is we'd shift these items, then we'd create a new item. Let's call it x again. But now we have a problem, because we have to update the index of x. So y is no longer at index 1. The new x is. And then y is now at index 2, and z is at index 3. The computer doesn't do this automatically for us. So we have to shift all of our items ourselves to the right so that now they are properly indexed. So z now would also be 3. Okay. So again, an insertion anywhere in the list, in the worst case, will cause us to move everything in the list after it. And let's say there are n items in the list. Well, we're dealing with n items again that we're shifting. Each individual shift is very easy to do, so that costs nothing pretty much. It costs 1 unit of work. So that's n units of work in total in the worst case. So our insertion algorithm also takes n time. And now for a little bit of a practical example. For those of you who have maintained lists of items in a Microsoft Word document, you know that if you wanted to add another item in between two list items that you already have, you're going to have to go and change the numbers to every item that follows. So that's pretty much exactly what the insertion algorithm is like. All right, and same thing for removal, right? Let's say we remove an item. Well, we're gonna bring these closer together. Now we have to update these indices again because they're incorrect. So overall, that'll take and work also. Okay, now let's look at the linked list. So I'm gonna copy this table again and analyze the linked list's performance. So if we want to search for something in a linked list, the process is the same as in the array list. We're gonna have to look at everything and find the position or the node that contains our number. So if I was to draw that, it'd look like this. It's not X, it's not Y, bam, it's Z. We found our number. Then I'd return the node. So again, as with the search in the array list, this costs n time because if there are n items in the list, there are going to be n units of work done. Okay, let's look at insertion. So if I want to insert an item, I'm going to take this and insert a new item, pretend that's a new item. And all I have to do really is create a new node, point the previous item to that new node, and then in the new node, point to what the previous item was pointing to. So in short, it's pretty much, you can figure it out for yourself, but it's pretty much just working with these things called pointers. And that'll never depend on the amount of items in the list. I can continuously insert right after X over and over again and just do the same amount of work all the time. So we call that a constant amount of work, and we denote that with 1. Okay, let's simplify and say 1. It could be 5, but that doesn't really matter too much for us. Something is really expensive if it depends a lot on the amount of items in the list, not if it has a high cost. Cool. Now, removal is going to be pretty much the same thing. You just play around with some pointers, and bam, we have constant time removal as well. So you can really see how a linked list is better than an array list. Now, that's not to say an array list is not good, because there's a bunch of nuances when it comes to an array list. Like, let's say I'm inserting to the end of the list. Well, that's usually what people do for the most part. And that takes a constant amount of work as well. So in some cases, not in the worst case, but in most cases, insert is going to cost only 1 unit of work, even in an array list. So practically, it's a pretty good data structure, and it's really widely used. Now, something I want to talk about is this cost, right? So up until now, I've been talking about the worst case cost. If you look on the internet, when people talk about worst case cost, they tend to denote the cost, like N, by putting an O before it and adding parentheses. This denotes that we're looking at the worst case, but I've been kind of implying that that's what we're doing here. So I didn't put the O's there. We're going to talk about these O's in another video, and we're going to be talking about algorithm analysis in that video. But the scope of that is a little too big to fit into this video, so we'll leave that for later. Now let's quickly glance at another abstract data type, the map. Okay. So here we have the map. So the map is pretty much a collection that literally maps a key to a value, or like a name to a thing. So let's say I have a map of all the students in the school and their grade. I would look at the map and then find the student's name so that I have immediate access to their grade. It's a very useful abstract data type. So we have things like the hash map, and then we have things like the red-black tree map. So the point is, across all the data structures that we have for a specific abstract data type, they all do the same thing, but they just perform differently. Data structures exist because you will need different performances for different use cases. That's all I have to say about abstract data types for now, but I will make videos later on about how to implement specific data structures, because I really like data structures and they're really cool, especially the red-black tree. All right, thank you guys for tuning in.